Okay, in this tutorial, we're going to talk about Lagrangian mechanics and how to apply Lagrangian mechanics to solve for the equations of motion of a spring pendulum system using Matlab, of course. So, of course, I just need to show this figure before I start deriving the equations in Matlab, just to give you an idea of what we're doing here. There's a lot of videos showing how to solve these equations by hand, but I'm going to show how to do it using the symbolic toolkit of Matlab. But just to give you an idea, here is Lagrangian equation of motion. You'll notice that it uses energy instead of forces, which is what Newtonian mechanics is based on. The capital T and the capital V is the kinetic and potential energy respectively. In this case, the kinetic energy is made up of how fast the pendulum is moving tangentially and how fast it's moving normally. And you also have to define part of deriving Lagrangian's equations of motion. The first step is to define your generalized coordinate systems, which I have shown here in green and red, the normal and tangential. You'll have to remember that the normal is always going to be normal to this pendulum, and the tangential is always tangential to it. It's not like x and y, where x and y stay still. And it makes the solving for the equations much simpler. So basically the basic form, and the q is the generalized coordinate, and j, the subscript j, is 1, 2, 3 to m. So it's, in this case, j goes up to 2. So we'll have two equations of motion based on the two generalized coordinates, the normal and tangential. Okay, so the d over dt is just the time derivative of the partial derivative of the kinetic energy with respect to the q dot time derivative of the first generalized coordinate minus this second term, which is kinetic partial derivative of kinetic energy with respect to the generalized coordinate, and then the partial derivative of the potential energy with the generalized coordinate, and it will equal 0, which is the right hand side. The kinetic energy, we said, is going to be basically the dot product of the velocity vector. The velocity vector will have two components. We'll have a normal and tangential component, and the potential energy will be made up of course, two components, one due to gravity and the other one due to the spring constant. The gravity component of potential energy is mgh, and h will take the here in the resting position, and the spring, the potential energy of the spring is just 1/2 kx squared. How much the x is how much the spring has deviated from its resting position. In this case, I'm going to call it del, del, and theta is just theta, obviously, the angle of the spring pendulum from this normal axis, or the y-axis, or the perpendicular axis, or whatever. And g is gravity pointing downward. M is the mass of the pendulum. K is the spring constant. And L, which is not shown in this figure, is just the length of the pendulum in its resting position. So that's just an overview. And next we'll go to Matlab and start solving for these two equations. There is going to be two, as we said. because there's two generalized coordinates. We need two generalized coordinates to fully define this system. Okay, let's go to Matlab. Okay, now we're in Matlab, so I have a file saved, the M file, saved on my desktop in a directory called Spring Pendulum. So first we will clear the window and then clear all variables and then define them. And it looks like I ran it over here, so let's run using F5 or run here. You can run it either way, it'll clear your variables. See, the workspace variables are now gone. Okay, so we'll use the Sims toolkit. First we'll define the mass as real, and then we'll define gravity as real, and then we will define the spring constant as real, and then we'll define the length of the pendulum as real, and define the del as real, or the normal distance of the pendulum away from its resting position, or away from the length L, and then the velocity in the normal direction, which will be the time derivative, or del dot. We'll call that del D real. And the second time derivative, or the acceleration of how fast does the pendulum accelerate in the normal direction, del double dot real. And then we'll do the same for theta. So the angular location will be defined as theta real, and then the angular velocity, theta dot, will be also real, and Sims theta double dot, which will be the angular acceleration. And now we define all our symbolic variables. So next we need to define the generalized coordinates, which we said are going to be the normal and tangential, and I'll just use unit vector notation to define these. So we'll say that the E underscore tangential will be 1, 0, and E underscore normal will be 0, 1. I'm just defining the normal and the tangential components, or the generalized coordinates. And now we need to start by defining the velocities in the normal and the tangential directions. Okay, back to our diagram here. We just referring back to it to know how do we define the velocities in the normal and tangential direction. In the normal direction, it's pretty simple. It's just going to be the time derivative of del, which is the distance that the pendulum moves away from the uncompressed length of the spring pendulum, or how much is the pendulum getting compressed and not compressed. And in the tangential, we just use r omega, which is the radius of this arm, times omega. Omega is the time derivative of theta. So with respect to the variables we have here, it's going to be L plus del times theta dot. Okay, now let's express what we just defined for the velocity in Matlab here. So velocity of the pendulum in the tangential direction is, we said, L plus del times theta dot. And in the normal direction, it's going to be del dot this is RW, and the other one is just the time derivative of del dot, or the time derivative of del. Now we'll define the velocity using the unit vectors. So it's going to be the tangential component times the unit vector in the tangential direction plus the normal component times the unit vector in the normal direction. And let's run that. Okay, no errors. Great. Okay, next we get the kinetic energy of the system, and the kinetic energy we said is 1/2 mass times v squared. Since v is expressed in vector notation, we need the dot product of v dotted with itself. So it's the capital T equals 0.5 times mass times the dot product. Dot's a built-in function of Matlab of VB comma V underscore B, and we'll run that and see what we get. Okay, this figure will help you visualize the gravitational component of the potential energy. It's just basic trig. It's the difference between the figure on the left and the figure on the right. The figure on the left shows the spring pendulum in its resting position, and this figure on the right shows it some instant later after it has expanded by del. So the difference, if we take the bottom of the pendulum in the resting position right here as your datum, so the difference you take L plus del times the cosine of theta, and you subtract that from just L. So that's the explanation. Okay, now we'll show the potential energy equations, which is made up of two parts: the potential energy gravitational and potential energy from the spring. Potential energy gravitational is mass times gravity times the difference between L and L plus del times the cosine of theta for reasons that we just showed. And then the spring gravitational is 0.5 times spring constant times del squared, and the total potential energy is the sum of those two. Okay, so we can run that and see our kinetic and potential energies. Let's not see this one. Okay, there's the kinetic and potential energy in terms of mass, theta dot, and theta and del dot. So now we have the energy equations related to our variables. So we are ready to plug all of that into Lagrange's equation of motion. Back to our figure and our equation. Here we derived terms, the T and V, kinetic and potential energy respectively. Next we need to find the kinetic energy, the partial derivative of the kinetic energy with respect to Q dot, which is the same as theta dot, and we need to find the time derivative of that. So when we take the time derivative of this term, we need to use the chain rule, which you will see in a second. And then this is just the partial derivative of theta, not theta dot, just theta. And this is the partial derivative of the potential energy of just theta again. So we'll do that in Matlab. Okay, the next thing we need to do is derive the partial derivative of the kinetic energy with respect to each generalized coordinate. So first we'll do it for theta, and then we'll do it for del. So basically it's the partial derivative of t. So if we run it, t is your kinetic energy. So basically we're going to differentiate this term with respect to theta dot. I think I said theta before, I meant theta dot. So we can simply use the diff function in Matlab. So partial derivative of kinetic energy, partial derivative of theta dot equals diff, and the first argument is t, and the second argument is the variable that we're going to use to differentiate. So if we just run that, you're basically going to take the derivative of kinetic energy with respect to theta dot. So you can see. Now we need to take the time derivative of this function. So the time derivative is, you have to use the chain rule because you have several things dependent on time. Like mass, of course, is not changing with time, neither is the length, but del and theta dot are changing with time. So you have to multiply by the inside. So we say d of pt theta dot dt is going to equal, differentiate this, just keep it copied, comma, with respect to any variable that depends on time. So theta, and then we have to multiply by theta dot. We can use this plus and ellipsis, and then differentiate it with the next variable, which will be theta dot, and we'll multiply that by theta double dot, and then the next variable will be del times del dot, and the next variable will be del dot times del double dot. Now let's take a look at that term. Of course, some of them will be zero because we see here theta dot and del only appears. So when we differentiate this term, or this, this term, with respect to theta double dot, it'll be zero. Or with respect to just theta, it'll be zero. Or if we differentiate it using del dot, it'll be zero. But just to keep all the terms there, we write them out. Okay, so it's not too bad. Next, we just need the derivative of the kinetic energy with respect to theta, not theta dot, just theta. So we can just copy this term from here. Just need to change the without just theta and not theta dot. And then we need the partial derivative of the potential energy of with respect to just theta. Okay, so the first equation, we'll call it equation 1. The first Lagrangian equation of the first generalized coordinate, or theta, will just be the sum of these three terms, or actually this term minus this term plus the last term according to our equation. And since it's conservative forces, the capital Q1 term on the right hand side just equals 0, because the forces acting on the system are conservative forces. Okay, so we take this term, subtract the second term, and add the last term. And let's take a look at what equation 1 looks like. So that's our first equation. Okay, that's the first equation with respect to the first generalized coordinate, which is theta. So we're going to repeat the same process using the second generalized coordinate, which is del. So same exact process. So we take the partial of the kinetic energy with respect to del dot, and that's just going to equal, take the derivative d comma del dot. And now we need to take the time derivative of this term. So we'll say d dt of this term. Now we have to do the same steps. Take the derivative of that term and then use the chain rule to multiply it by anything that depends on time. So we have to go through our four variables: theta, theta dot, del, and del dot. The derivative of the inside. And now do it again for del. And finally for del dot. And that's that. That's the first term of the Lagrangian equation. Okay, now second term is the partial derivative of the kinetic energy with respect to just del and not del dot. So we call it this. And now the final term is the partial derivative of the potential energy with respect to just del, or the second generalized coordinate. And equation 2 will equal the first term minus the second term plus the third term. Put some semicolons. And let's see our two equations of motion. Okay, here are the two equations of motion for Lagrange, two Lagrange's equations of motion for a spring pendulum. And I'll create another video showing you how to solve these equations using Matlab's ODE function. But for this video, I just wanted to symbolically develop the equations using the Sims capability in Matlab. Okay, that's it for this one. Thanks.